So now we're going to move into momentum, okay? Momentum seems like a really strange concept that comes out of nowhere. All we're going to do is multiply a mass by a velocity, which should have you thinking back a little bit to the center of mass from before, but we're going to get there. Momentum doesn't seem very useful at first until you realize that the conservation of momentum, which I'm going to get to here in a second, conservation of momentum should remind you a little bit about conservation of energy. Conservation of momentum is even more powerful. Conservation of momentum is even more powerful. So it's going to let us solve problems that we would not have been able to solve using conservation of energy. And it's going to go back to that idea in the previous interview of the external versus the internal forces. Okay? So if all those interactions are internal, then I can ignore everything and focus on the velocity of the center of mass, which will then allow me to focus on conservation of momentum. Okay, so let's start off with what exactly is momentum. Well, momentum is given with the letter P for momentum. I know, we couldn't use them again, I'm sorry, but P stands for momentum. It is a vector quantity, and it is equal to the mass of the object multiplied by the velocity. Mass is a scalar quantity, so I can multiply that by the velocity, which is a vector, and that gives me the momentum as a vector quantity. Now, momentum doesn't have any special units. I have not yet written a physics book where I've decided to call this a Stein, which sounds pretty damn cool if you ask me. But for right now, this is just a kilogram multiplied by a meter per second, so a kilogram meter per second. There's no special unit for it, okay? Now notice something here. If we look at the force equation, force is equal to mass times acceleration, you guys know that the acceleration is the time derivative of the velocity. So that means over here that now I've got m dv dt, or since mass does not change with time, I can just fold that back in here, and now I'm just going to have that the time derivative of momentum is equal to the force. This is actually the way that Newton described Newton's second law. He did it using momentum. He did not use acceleration. Okay, that is important. That's something that comes up in higher level mechanics because the math starts getting a little crazy, but we don't really have time for that. Okay, now this also works for a system of particles. So the momentum for a system of particles is equal to the total mass, capital M, multiplied by the velocity of the center of mass for those particles. Now notice how powerful this is right now. Go back to the previous video. Unless there are external forces, this velocity of the center of mass will not change. What that means is that the momentum will not change. That is going to lead to momentum conservation, conservation of momentum. Okay. Now, impulse is a really fancy name given to the change in momentum. Impulse is the change in momentum. Now, impulse is given as J, that is the variable for impulse. I know we couldn't use I, that's going to come up with rotational inertia, and that's when you're all going to get very mad at me because that's the hardest stuff of the year, okay? J stands for the impulse or the change in momentum, and that is equal to the integral from some time initial to some time final. Okay, those are times right there. Sorry for the sloppy handwriting. That's going to be time final, time initial. Some force that changes with time, and we are integrating that force with respect to time, and that is equal to the change in momentum. Now, a little trick for the AP. If you see a time variable force, then most likely you are going to be dealing with momentum. In the previous chapter, we dealt with a position varying force, and we integrated that force with respect to position, and we used that in order to get the energy, the work. Here, if your force is given as some function of time, that means you should probably be focusing in on momentum, okay? Probably focusing in on momentum. Now, if we just have some constant force here, if this force is constant and it's not changing in time, that makes life very easy. The impulse is given as the force multiplied by the time interval. Okay? Now again, notice that the impulse is a vector quantity. That makes sense because it is the change in momentum. And that would be a force multiplied by some scalar. The scalar in this case, is time. So what this means here is if the force is not changing, in time, then all I have to do is multiply it by the time, and I will get the change in momentum. Okay? Now that should make sense to you, because remember, force is equal to mass times acceleration, and all we did was multiply acceleration by time to find the velocity of something. Think back to the big four equations. Go take a look at your notes. Right now, if you need to, you can pause this video. That is okay. But if you think about it, we multiply an acceleration by a time interval to figure out the change in the velocity. Here, all I've done is add mass, where this is now equal to delta p, the change in momentum being mass times velocity, and here the force being mass times acceleration. Okay? Now the big deal, the conservation of momentum. In the absence of external forces, okay, so we have no external forces. I'm not coming along and picking up one of the pool balls down at the student center. In the absence of external forces, that means that the net force would then be equal to 0, no external forces. That means that the momentum is constant. The momentum is constant. So if there are no external forces inside the problem, that means that the momentum is going to be constant. That is hugely important. Now let's do a couple examples just to make sure that we've got this idea of momentum and how it's impacting all of our various problems. Let's say in one example, we have an average force of 5 newtons, a time of 10 seconds, and a mass of 2 kilograms, and we want to find, from an initial velocity equal to 0, we want to find the final velocity. So we have an average force of 5 newtons, time interval of 10 seconds, mass of 2 kilograms, the initial velocity is 0, and the final velocity over here is what we're trying to find. Now yes, you can solve this with basic kinematics. Divide the force by the mass to find the acceleration. You know that the acceleration is constant in time, and you know the time interval. You can use your big four equations to figure out the final velocity. But you can also just use momentum and impulse to find the same answer. It's just as fast. So the change in momentum is equal to the force, average, multiplied by the time interval. So that's going to be 5 newtons multiplied by 10 seconds. So this reveals that another form of the units for momentum is a newton times a second, which makes sense because a newton is a kilogram meter per second squared. Now we're multiplying that by a second. And back before, we said that the units for momentum were just a kilogram meter per second. So we've stayed consistent with all of our units. So this will give me my change in momentum. So that's going to be equal to 50 newton seconds, okay, or 50 newtons per second, or excuse me, Newton seconds. Sorry, somebody's yelling at me already. 50 Newton seconds, do not confuse that with nanoseconds, or 50 kilogram meter per second. And now that is equal to the final momentum minus the initial momentum, okay? The initial momentum was 0 because the initial velocity was 0. The final velocity is what we're trying to find, and that would be the momentum final is equal to the mass times that final velocity. So 50 divided by 2 kilograms gives us a final velocity, sorry this went down so low, of 25 meters per second. So this is another way of finding the final velocity instead of using the kinematic equations. Can you use the kinematic equations? Yes. But if it's a time variable force, that can start to get a little dicey. Yes, you may be able to divide by the mass, but sometimes you won't be able to. What happens if you don't have the mass? That could create a problem, okay? So now, last example for this part. let's use a time varying force. So the force as a function of time is 5t squared plus 2t plus 10. And let's keep that all in newtons. 5t squared plus 2t plus 10. And we want to find the impulse over the first 2 seconds. So find the impulse over the first 2 seconds. We need to integrate this force because it has been given to us as a function of time. We also don't know the mass, so we can't rely on any kinematic tricks right here. So that means that we're going to come over here and we're going to integrate. So the impulse is equal to the integral from 0 to 2 because I'm going for the first 2 seconds. The force in this case is 5t squared plus 2t plus 10. We're integrating with respect to time. So that means that we are going to have 5t cubed over 3. 5t squared, the t squared goes to t cubed. We need to divide by 3. 5t cubed over 3 plus t squared. T to the first power goes to t squared. And we already have a 2 down in front, so that looks good. Plus 10t. Remember, I do not need to include the constant because this is a definite integral. It's going over limits of integration, 0 to 2. And so now I get that the impulse is equal to 37.33 kilogram meter per second. So all I've done here is find the impulse, the change in momentum, using a time variable force. To recap, we've talked about momentum. Momentum is equal to mass times the velocity. It is a vector quantity. Impulse is the change in momentum. That is done by either integrating a time variable force with respect to time, or by just multiplying a constant force by the time interval. The conservation of momentum is extremely important, and that conservation of momentum comes in the absence of external forces. So if the net force equals 0, there are no external forces in the problem, everything is internal, and that means that the momentum is going to be constant. The momentum you start with is going to be equal to the momentum that you end with. Now I'll give you guys a hint. On some of the problems, you have situations where like somebody standing on a raft jumps forward, and the raft is going to move out from under them. And they're going to ask you for what is the velocity of the raft. And people are going to come up to me and say, well, what am I supposed to do on this problem? Think about it. The raft and the person on top of the raft are interacting with each other, correct? So there's no external force in the problem. The raft is allowed to impact the person, and the person is allowed to impact the raft. What did the momentum start with if the raft and the person were standing still? The momentum initial is 0. So that means that the person jumping forward now has a velocity in their mass, that's their momentum, and the raft has to move in the opposite direction with its own momentum in order to cancel out the momentum of the person. There's a couple problems in the homework about that. This should give you a hint for how to start some of those.